Hello everybody, and welcome to part 2 of our bearing capacity lesson. Now again, this is following up from the part 1 lesson on bearing capacity, and so if you haven't watched that lesson yet, please stop this video and go watch part 1 first, because otherwise what we talk about in this video isn't going to make much of any sense at all. So we're just going to pick up where we left off from the last video. Now, in the last video, we introduced you to the idea of ultimate and also allowable bearing capacity. Geotechnical engineers will generally design to allowable bearing capacity, but all allowable bearing capacity is the ultimate bearing capacity that's been adjusted for some kind of factor, safety, or a load resist or a resistance factor if you're doing LRFD. Now, what I want to talk about is the difference now between gross and net bearing capacity. So, follow my logic here. On the left here, I have a diagram of a footing in some granular soil. Now, the soil that's here beneath the footing, that soil, honestly, does not care what is causing the stress on it. It could be a footing, it could be an embankment, it could be more soil, it could be anything. The point is, to the soil down here, it is simply stress. And the soil can only take so much stress before it develops shear planes. And therefore, we have to account for how much load we can actually really place on the footing. So to geotechnical engineers, that's great. But you have to understand that geotechnical engineers work very, very closely with structural engineers. And all structural engineers care about is this guy right here. This is the column load, or the amount of structural load that can be placed on the column and sent down to the footing. And so what we need to do is to convert the bearing capacity that the soil can handle to an equivalent column load, or what we're going to call, if we want to keep it in terms of a pressure, a net pressure that we can give to the structural engineers. So in other words, gross pressure essentially represents the allowable bearing capacity. Okay, net pressure is going to be the allowable minus all the inherent stresses on the soil. And what do I mean by inherent stresses on the soil? Well, let's look at this for a minute. So obviously we have the column loads, and you're going to see a little D and a little L. So the D stands for dead loads and L stands for live loads. But in addition to that, we also have the weight of the footing and the column itself. Now, those may not be things that the structural engineer really cares about, but they still have to be accounted for because they apply stress to the soil. And also, we could have the stress from any soil that is backfilled on top of the footing. So that also is applying weight and needs to be accounted for. So all of these different stresses, meaning the column loads, the weight of the footing, and the weight of the backfilled soil, those are all the inherent stresses. And essentially what we're saying is that the allowable gross bearing capacity is going to equal the ultimate gross bearing capacity divided by some factor of safety. And we have to say, or good design is that the allowable gross bearing capacity is going to be greater than, or the minimum equal to, all of the weights divided by the square or the footing area that's placed on the soil. So How in the world do we calculate that? Because that means that we need to calculate the weight of the footing, the weight of the column, the weight of the soil, and it can be a lot to account for. So often geotechnical engineers are going to make some pretty simplifying solutions. So let's do a little bit of math here. Here's our starting equation right here. We're going to say that the allowable net bearing capacity is going to equal the ultimate gross bearing capacity minus the overburden divided by the factor of safety. Well, okay, minus the overburden. So remember, typically we say that overburden stress is equal to the unit weight of the soil times the depth of the footing. Okay, well, what do we do about the concrete? What do we do about the weight of the column? Well, we're going to make a pretty gross assumption here. We're going to assume that the unit weight of the soil is approximately equal to the unit weight of the concrete. Is that true? Well, no, not really. I mean, unit weight of soil is generally in the order of 125 pounds per cubic foot. Weight of concrete is usually on the order of about 160 pounds per cubic foot. And so is there a difference? Yeah, it's a pretty substantial difference. But that's okay, because any errors in our calculations are going to be caught up in this massive factor of safety where we said it's going to be 2.5 to even 3.0 at times. And so with that giant factor of safety, any error that we get by this simplifying assumption is going to go away. So we're not going to worry too much about it. So if we make that simplifying assumption, then we basically say then that the unit weight times the depth of the footing is equal to our overburden, and that's going to be approximately equal to the weight of the soil plus the weight of the footing and column, all divided by the cross-sectional area. And if we make that assumption, therefore, we have this final equation, which is that the allowable net bearing capacity has to be equal to or greater than the dead and the live loads divided by the cross-sectional area, or the footing area of our footing there. Another topic. What if we have footings on clay? Now, in previous lessons, I talked a little bit about the challenge then with clay is understanding whether or not we treat it as an undrained or a drained material. If it's undrained, there's the potential for pore pressure effects to generate, and we have to account for those. So this really is the question, right? Do we consider the soil to be undrained, where we have a friction angle equal to 0 and we just rely on the undrained shear strength of the soil? Or do we assume that the soil is drained and we have a drain friction angle and we have the drain cohesion? Now, here's my rule of thumb, and I'll share it with you. In general, if the clay generates positive pore pressures when you shear it, in other words, when you shear it, it tries to contract. And this is generally what we see in normally consolidated clays or in sensitive clays. If you see that kind of behavior, then in general, the effective stress is initially going to decrease when we load it. So in other words, as we shear it, pore pressures are going to generate. They're going to go up because the soil is trying to contract. Pore pressures go positive. Effective stresses decrease as a result. If you'll remember, the equation for effective stress is total stress minus the pore pressure. Therefore, if pore pressure is positive, that means that effective stress essentially is going to go down in order to keep the equation equal. Okay, so if my effective stress decreases, that's going to also decrease the shear strength of my clay. Therefore, when I have a contractive clay, The critical case is immediately after I load the footing, and that's typically around the end of construction, or we call it the end of construction case. And so that's going to exist when we have excess pore pressure still in the soil. So if that's the case, we're going to assume friction angle of 0, and because of that, we're going to use these bearing capacity factors right here. If I plug those into, say, the bearing capacity equation for a strip footing and simplify it, I get this beautiful, wonderful equation. So this is the equation that you're going to use if you have a contractive clay for bearing capacity. And now remember, that's anytime you have a normally consolidated clay or a sensitive clay. Now, that's for the ultimate bearing capacity. What if we want the net bearing capacity? Remember, net, we're going to subtract the overburden stress from the soil. So this gets really convenient because notice we have a Q right there in our equation, and net is simply ultimate minus Q. So if I subtract a Q from this equation right here, then it gets really simple. So that equation that I've circled right there, the net bearing capacity, that is the bearing capacity that we can give to the structural engineers and that they can use to help determine how much stress they can actually put on the soil after they've already accounted for all of the backfill and the weight of the footings and the columns themselves. Okay, well that's nifty. Now, what if I don't have a contractive clay? What if I have a dilative clay? Now remember, a dilative clay is generally an over-consolidated clay. And I'm not talking about lightly over-consolidated clay. I'm usually talking about a pretty heavily over-consolidated clay, like OCRs on the order of, I would say, greater than 2 or 3 even. So if you have clays that have an over-consolidation ratio greater than 2 or 3, it's likely going to be dilative when you shear it. And if that's the case, then we're going to see increase effective stress when we initially load it. So remember, according to our equation, if pore pressure goes negative, then that's going to, or actually if pore pressure goes down, that increases effective stress in order to keep equilibrium in that equation. So if pore pressure goes down, effective stress goes up, then what we're going to see then is that the near term or the short term effective stresses right after we apply loading are actually going to be higher than they are in the long term. That's because the soil creates a vacuum effect. Imagine trying to shear soil, but because of the suction that's going on in the soil, that suction makes the soil seem stronger than it really is. That's really what's going on. It's the same phenomenon when you stick a shovel into saturated clay and you try to lift it. That clay in your shovel feels really, really heavy. And it's not that it's heavy, it's that you can't shear it and lift it out of the ground because the suction in the clay is holding it together. It's the same phenomenon. So if that's the case, it wouldn't make sense to design for that case where you have suction and a vacuum in the soil. You're going to want to design for the long-term condition when all of that suction has gone away and you're just relying on the strength of the soil by itself. If that's the case, then you're going to use the long-term conditions and you're going to use the drained cohesion and the drained friction angle, so the drain case. So if I have contractive clay, normally consolidated, sensitive clays, those kinds of things, we're going to use undrained shear strengths and phi equals 0 conditions. If I have dilative clay, so this would be like over-consolidated or heavily over-consolidated clays, I'm going to use drained shear strengths. Okay, now, if you remember that we could get significant deformations in the soil before it actually generates a shear plane and fails in bearing capacity. Now, the question I want to ask is what if this intermediate deformation is more than your structure can handle? In other words, I'm on the way to bearing capacity failure, but I don't actually reach it. But maybe just getting there is still more than my structure can handle. So for this reason, we often develop what we call bearing capacity charts. Now these charts are going to plot both the allowable bearing load and also the load associated with different levels of settlement. That's right, settlement like we talked about before. But we're going to do it as a function of size of the footing. So in other words, you can imagine if I don't know the size of my footing, but I just use Terzaghi's equation for bearing capacity, it's really just a linear function. Now let's see if I can remember it. There's going to be a C and an NC term, and there's going to be a Q and whoops, that's not a Q, that's a gamma. There's going to be a Q times an NQ term, and then there's going to be a 1/2 times beta gamma times the N gamma term. Okay, so that's roughly Terzaghi's equation for ultimate bearing capacity of a strip load. Now you can see that if I know all of these terms except the width of the footing, then that means that this just becomes a linear equation where these terms right here basically become my y-intercept, and this becomes my dependent variable with the slope of the line. So if I plot Q ultimate as, and then, well, let's see, because I want it to be allowable, so then let's say that I take this whole thing and then I divide it by a factor of safety, and that's not going to give me ultimate, that's going to give me allowable. There we go. If I want allowable bearing capacity, and so I now have a factor of safety, you can see that I would just plot a straight line. It's a straight line, and the slope of that line is simply equal to, oops, that's not right. It's simply equal to 1/2 gamma times N sub gamma. It's this term right here. And that equation, right, that y-intercept right there is equal to C N sub C plus Q N sub Q. Oh yeah, divided by a factor of safety. Can't forget that. So it's just simple algebra, folks. That's all I'm showing you right there. So it's just a straight line. And that is the function of Q allowable for bearing capacity. Okay, well that's just dandy. But what if I have a sandy soil and I also want to know how my elastic settlement changes as a function of footing width? So I could go and I could take the Meyerhof empirical equation for elastic settlement of a footing on sand, and I could plot that as a function of footing width for a given settlement. And so in other words, say that elastic settlement I lock at 1 inch, and then I just rearrange the equation such that I solve for Q given footing width. So if I do that, then I get a function that looks curvy like this. So what does this mean? I have two curves now on this plot. What this means is that I am simultaneously considering bearing capacity failure and some allowable or tolerable settlement in one single plot. And as the engineer, this means that if I want to know how much stress I can apply on a footing of a given width, I can go to this plot, and all I need to do is take the lower envelope or the lower bound of these two curves, and from this envelope here, it will tell me what my allowable bearing pressure is for that footing width. So in other words, if I'm over to the left of my intersection point, so if I'm over here to the left of it, I'm falling on the bearing capacity line, which means that bearing capacity is going to control my allowable bearing pressure, not settlement. In other words, even though I have settlement line up here, I'm going to have a bearing capacity failure or exceed my allowable bearing capacity before I have unallowable settlement. But if I'm to the right of my intersection between those lines, now I'm in the portion that's governed by settlement, which means that even though, it's saying, yeah, I can have up to this value of stress before I have a bearing capacity failure, this line right here is telling me that I'm going to exceed my allowable settlement before I achieve a bearing capacity failure. And so with this enveloped curve here, this envelope curve will tell us the allowable pressure that will limit undesirable deformations for our structure. We call these plots, by the way, bearing capacity charts, or bearing capacity design charts. And they're extremely useful, and geotechnical engineers commonly make these types of charts for structural engineers so that the structural engineers can size their own footings and determine what stresses they can place on those footings. So how do we develop a bearing capacity chart? Well, we have to consider bearing capacity and settlement as a function of footing size, computing the applied stress, or Q allowable. So this is going to be Q allow, this is going to be B for our footing size. So we have to develop equations that relates Q allowable as a function of B. Okay? Well, for this class, where we're just starting out and it's elementary geotechnical engineering, we're just going to look at uniform sand. So if I have a uniform sand, you'll recall then using the Meyerhof empirical equation from an earlier lesson on settlement. If I just revise or modify that equation, I can solve for Q as a function of footing width, B. The trick to making this work is I have to specify which settlement is tolerable. So in other words, I can say, yeah, my structure can handle 1 inch of settlement, or my structure can handle 3/4 of an inch of settlement, or whatever it is. I just have to put a value in there to define the tolerable settlement, and then back calculate which stresses will give me that settlement given different footing width sizes. Awesome. What if I don't have uniform sand? What if I have a uniform clay? Uh-oh. Well, if that's the case, then I'm not relying on elastic settlement. I'm relying on primary consolidation settlement. So that means then that I have to develop a spreadsheet and go in and basically create an iterative spreadsheet that will allow me to adjust the load and obtain a desirable settlement for all of my different soil layers in computing consolidation settlements. So it's a little bit of work, but I'm confident that if you had to do it, if you were assigned to do it for your work, you could figure it out. Now what if I have layered soils? In other words, both sands and clays, or gravels and clays, or sands, gravels, and clays. If that's the case, I have to use a combination of elastic and primary consolidation settlements for this exercise. It becomes a little bit messy. So we're not going to touch it and talk about it here, but I think you get the idea of how you would pursue that type of thing. So let's go ahead and develop an example bearing capacity design chart. So here's a problem I've given you. It's a square footing. It's in uniform sand. That's nice. We're going to develop a bearing capacity design chart for a maximum allowable settlement of 1 inch. That's what our target is. Okay? Let's say that the footing is at a depth of 3 feet below the ground surface. Now we could do it for different depths, but we're just going to focus on a depth of 3 feet. And we're going to assume a factor of safety for our bearing capacity of 2.5. So our problem looks something like this. Okay? My saturated unit weight of the sand is 125 pounds per cubic foot. My moist unit weight above the water table, so remember, here's the water table right there. My moist unit weight is at 110 pounds per cubic foot above the water table. I'm going to assume a field standard penetration test blow count of 37 blows per foot. And so if I use the Peck, Hansen, and Thornburn chart from the Part 1 bearing capacity lesson that you watched last time, I could use that chart and it would tell me that I would get a drained friction angle of about 38 degrees for that level of SPT blow count. Then I could go to any design chart. Now for 38 degrees, we're going to assume that this is a general shear case, not a local shear for bearing capacity. So I could go to any of my tables or bearing capacity charts, and I'm going to pick off values of N gamma and NQ. So you're welcome to go back and look in your notes or look in your textbook to get these values, but I'll just tell you what I got. For 38 degrees, I got N gamma of 78.61 and NQ of 61.55. Now what about N sub C? Where's that? Well, remember, because this is a sand, we're going to say that C equals 0. And because C equals 0, the cohesion equals 0, I don't need to worry about N sub C. So I'm not even listing it here. So here we go. First of all, let's develop our plot or our function for settlement. So I'm going to use the Mayer-Hoff empirical equation for computing allowable bearing pressure given an allowable settlement as a function of footing width. So here's my modified Mayer-Hoff equation for elastic settlement, and now I'm just going to start plugging in numbers. So I know my allowable settlement is, that's right, 1 inch. So I'm going to plug 1 inch in there. Now remember, by the way, this Mayer-Hoff equation is empirical, which means that you have to put in the units that match what Mayer-Hoff specified. The units are not consistent in this equation. So settlement has to be in inches. And Q has to be in kips per square foot. And footing width, B, and depth of footing have to be in feet. Those are the units. I know inches and feet, they don't mesh out. And pounds per square foot and kips per square foot, they don't mesh out either. But don't worry about it. It's an empirical equation. Okay, my blow count N. This is given to me in the problem. It was equal to 37, so I throw that in there. Depth of footing, I know that was equal to 3 feet. So I can put that in there as well for depth of footing. Now what do I put in for B? I don't put anything in. It's unknown. That's my dependent variable. So I simplify this equation right here. I simplify it as a function of B. And I'm done. Okay, so now I have my equation for my settlement portion of my bearing capacity chart. Now, one thing I want to point out, because at this point, some of you are saying, wait, where's the factor of safety? Don't I need to apply a factor of safety to that settlement? No, 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 no. Don't be tempted to do it. We do not, I repeat, we do not apply a factor of safety to the settlement or to the back calculated pressures for settlement. We don't do it. The factor of safety applies to bearing capacity, not settlement. So do we apply any factor of safety to settlement? No. The standard of practice is no, we don't. We just leave it as is. And that's because we've become very, very confident with our ability to compute settlements. Okay, so no factors of safety to the settlement curve, guys. And on the final exam, I don't want to see you do that. The factor of safety applies to the bearing capacity portion, not the settlement portion. Okay, speaking of, let's do the bearing capacity portion. So again, we're going to assume net bearing capacity for this example. And it's a general shear case because our friction angle is greater than 36 degrees. So for a footing depth of 3 feet and water is right at the base of the footing, we're going to use the buoyant unit weight for the frictional component of the bearing capacity equation below the bottom of the footing. And we're going to use the moist unit weight for the portion of the footing that is, or for the soil above the bottom of the footing. So remember, in our bearing capacity equation, you want to use the right unit weights. Okay, so here's our equation for the allowable net bearing capacity for a square footing, not a strip footing, a square. If it was a strip footing, that would be 1/2. But now it's 0.4 because it's a square footing. Okay, with this equation, now remember, by the way, this equation is for ultimate bearing capacity. Minus Q is what gives us net, divided by factor of safety is what gives us allowable. So we have allowable net bearing capacity. So let's just start plugging in. For our first terms, this portion is for the overburden. Remember, gamma times depth of footing is just simply Q. Okay? So we're going to use, for the subunit weight of the soil above the bottom of the footing, we're going to use 110 pounds per cubic foot. But to be consistent with the units that I want of kips per square foot, I'm converting this unit weight to units of kip per square foot, not pounds per square foot. That's why it's 0.110 instead of 110. Okay, depth of footing, we know that that's equal to 3. Okay, N sub Q, we got that from the table, and I gave that to you right up front. That was 61.55. Okay, this is the frictional component of the bearing capacity equation, and this gamma is the unit weight below the bottom of the footing. Because we're below the water table, we're going to use the buoyant unit weight. So that's simply the saturated unit weight, 0.125 kips per per cubic foot, minus the unit weight of water, which is 0.0624 kips per cubic foot. Now, remember, 62.4 is pounds per cubic foot, but we want it in kips per cubic foot. So I just converted my units. Okay, B is my dependent variable, so I just leave that alone. And gamma, I gave that to you at the beginning of the problem. We looked it up in a table. That's 78.61. And then minus Q. So this is the overburden stress again. So we're above the bottom of the footing. So again, that's the moist unit weight for this problem of 0.110 kips per cubic foot times the depth of the footing, which for this problem is 3 feet. Let's put feet on this one too. Okay. So if I simplify this problem down, I get it down to this equation right here where I haven't yet plugged in, I forgot the factor of safety of 2.5. Sorry, Thanks for reminding me. Okay, so if I simplify the equation and I don't put in the 3 yet for my depth of footing, I get this equation right here. And then if I want to throw in the 3 for the depth of the footing, I can. If I want to throw in different values for the depth of footing, I can. But the point is, I simplify it down to my linear equation for net allowable bearing capacity. So now I've got bearing capacity and I've got settlement curves. So using those two equations, I could create a table like this where I just take a range of footing widths and I go ahead and I solve for the allowable pressure for considering bearing capacity. So that's that linear equation from bearing capacity. And then I can also solve for the allowable pressure considering the allowable or tolerable settlement of 1 inch that I computed with the Mayer-Hoff empirical equation. And then for each of these footing widths, I just compute these different numbers. Now, envelope the allowable pressures from this table, and the lower of the two pressures governs. So in other words, if I pick a footing width of 2 feet, I've got 9.57 and I've got 31.22. Which one is lower? Yeah, the one from bearing capacity. That means bearing capacity governs, and that's the value that I'm going to use for design. What if it's 3 feet? Same, bearing capacity. That's the lower of the two. What if it's 6 feet? Same, bearing capacity is lower than the value from settlement. What if it's 8 feet? Uh-oh, I've got 14.29, I've got 13.17. We've crossed the intersection, and now allowable settlement is governing. So if my footing is designed for an 8-foot width, I'm going to base it on allowable settlement. And 13.17 kips per square foot is now my maximum that I can recommend. If I were to plot these values from that table on the same chart, they would look something like this. As an engineer, then I would probably just create a new plot and envelope it and give that plot of the envelope values to the structural engineer. So that means if I truly wanted to optimize the stress that I could apply on the soil, I would take the peak value where the curves intersect, and I would say, okay, Mr. Structural Engineer or Miss Structural Engineer, the maximum stress you can apply to that soil is about, from this one, I'd say 13 KSF. And you can do that at a footing width of about 7.5 feet or so. So you can see how these charts could be really, really useful and could allow the engineer to optimize a solution for their particular case. So yeah, these are fun charts to make, and engineers, bless me, I sneezed. Engineers find these charts extremely, extremely useful. So what do I expect you to be able to do on the final exam? And there's no way I'm going to ask you to develop a chart like that. That's crazy. But I could ask you to say, given a particular footing width, tell me what the allowable stress is to use for design. That means you would have to compute the point for bearing capacity and the point for settlement, compare the two, and then pick the governing one, whichever one is lower. So I can ask you to solve a problem for a single footing width on the final exam. I won't have any guilt over that one, but I won't ask you to develop an entire chart on the final exam for the course. Okay, guys, this has been a fun lesson, and it's been a fun opportunity to teach you guys some basic principles of soil mechanics and some basic stuff related to geotechnical engineering. Good luck in preparing for your final exam, and I look forward to seeing you guys when I return from Anchorage. So thanks for watching, and have a wonderful rest of your day.